Hello, my name is Mariano Sorgente. I work for Chia network, and today I'm going to be talking about proof of space Nakamoto Consensus using VDFs. So this is one of the interesting applications of VDFs that actually sparked a lot of research in VDFs. And it's worked by Chia network, advisors, and others, primarily Bram Cohen and Christoph Pietrzak, who is one of the authors of the RSA VDFs. So first, let me talk about what do I mean by proof of space Nakamoto Consensus. So in Bitcoin, we have a network of machines that perform SHA-256 over and over again. And 10% of the CPU power, 10% of the hash power in Bitcoin allows you to win approximately 10% of the blocks. And the fork choice rule, the chain that wins is the one with the most work on it. These are called miners. So what if we could do the same thing, but with storage? So let's say the network has 400 terabytes of storage. If a specific miner on the network has 100 terabytes, a fourth of the storage, he could win 25% of the blocks. So have a Nakamoto Consensus with longest chain wins, but with storage instead of with hash power. In our system, we call these farmers as opposed to miners, since it's an environmentally themed blockchain. So why? What's the point of this? Why use storage for consensus as opposed to hash power? Well, first of all, the decentralization of free storage is much higher than that of ASICs. ASIC manufacturers are very few, and also cheap energy is not very distributed. So that results in Bitcoin hash power being centralized in very few locations. Also, the low energy consumption is one of the biggest points. Bitcoin right now has a huge amount of energy consumption and only grows as the usage increases. So with space, you don't really need to waste much energy. All you need to do is look up a few things on disk and store data. And storing data doesn't require much energy. Furthermore, we want a Nakamoto Consensus system. So a Bitcoin-like blockchain. This is key. This means that it's objective. So you can look at two chains and really quickly verify which one has more work on it. With Bitcoin, you just verify the headers and see if the SHA-256 matches. No Byzantine agreement, no K agreement, no checkpoints, synchronization, registration, et cetera. So we're trying to create something that's very similar to Bitcoin, where if you find a solution, you submit it to the blockchain, you get your reward. Not something like a lot of the proof of space consensus algorithms, which are very different type of algorithms. So storage is a very, very nice thing. How do we achieve this? Well, the most important construction is a proof of space. I have to be able to prove that I'm storing a certain amount of space. This is not proof of useful data. I'm not storing people's files. I'm storing basically a bunch of random pre-computed numbers on my disk. So let me explain what a proof of space is. It has three functions: initialize, prove, and verify. Initialize takes in a public key and a size. So let's say I can initialize my hard drive of 100 terabytes, and I have to run this init function. Init might take hours, it might take days. It's not guaranteed to be fast, right? At the very least, you have to write your disk, which requires seeks on your disk. So initialize sets up your hard drive. Then there's prove. Given a challenge, I can compute a proof that basically means that I have this data stored. So a verifier can really quickly check whether I'm storing this data or not. One of the properties that we need from this is the proof and verify are efficient. So they need to be constant time operations. And the size of specifically the size of the proof needs to be constant size. So even if I have a plot of 500 terabytes, I should create a very, very small proof that proves that I have this data stored. Furthermore, one of the security requirements of a proof of space is that if the proof verifies, that means I actually have stored that data. I shouldn't be able to do time-space trade-offs where I only store 10% of the data and pre-compute things on the fly. So for example, I store data on my hard drive. Justin gives me a challenge. I can respond really quickly with a proof of space by just doing a few lookups on disk. And Justin can verify that actually I responded correctly. So I'm storing that data. Another important property is that the proof is unique. This is extremely important because otherwise there's a lot of attacks that I can do to create multiple proofs and basically pretend that I'm winning. And furthermore, a really nice property is that there's no registration required. That is, the initialization phase is non-interactive. There are a lot of proofs of space where the initialization is actually interactive. So for example, I would need to communicate with the blockchain and post a transaction before just to initialize the block. This is different from the Bitcoin model, where if you find a proof, you can instantly submit that to the blockchain with no registration. There's no interaction in joining the Bitcoin system as a miner. So that's a key requirement as well. And the latest paper, AAC17, actually achieves this non-interactive initialization phase. So how do we do a proof of space Nakamoto consensus? The naive way to do it is just replace proof of work with proof of space. Every 5 minutes, the best proof of space is chosen, proportional to each farmer's space. However, this is not secure at all. Specifically, creating a proof of space is instant, as I said. It's very fast. It's a constant time operation. So a miner or a farmer can just create a lot of different types of proofs, and create a really long chain. And it's very fast to create a long chain. So an attacker can basically fork the network since there's no time required for each proof of space. So this is different than Bitcoin, where you actually need to spend time hashing in order to create your proof. So of course, you could do something where people communicate and come to consensus on who has the biggest proof of space, but we're trying to create a Bitcoin-like system. So these long-range attacks where someone creates creates a long blockchain really quickly, this is what can be solved by VDFs. So how do we do this with VDFs? How does this help? So each block here contains two things. Instead of just a proof of space, each block contains a proof of space and a VDF output and proof. Both of these are unique. The proof of space is unique, and the VDF output is unique. And the way we compute the number of iterations, so small t there is the number of iterations. We do 0 point hash of the proof of space. So let's say a block height equals 1. There's a proof of space, and there's a VDF. So now let's look at height equals 2. Each farmer computes their own proof of space on their hard drive. And some farmers are going to have a really good one because their hash has a lot of zeros in front of it. So the number of iterations they have to do is very small. So 0 point hash times big T, which is the difficulty parameter. So this is kind of a way to, each farmer gets assigned a time for their VDF. Some people may get a really fast one, like 5 minutes. Some may get a really slow one, 160 or 1,000,000 years. And this kind of simulates a Bitcoin-like system, right? In Bitcoin, you can think of the system as each miner gets assigned a time. I will find my solution in 1,000,000 years. He'll find a solution in 20 minutes. Whoever has the smallest time is the most likely to win. So here we're simulating the exact same thing. Also, proofs of space, we can do it so that if someone has a really big plot, they get more chances, right? So they get more of these tickets, what we call them. And there's a way to change the formula so the more space you have a proportionally higher chance of getting a small time. But essentially, it's kind of like a lottery where each person gets a different number of iterations that they must execute. Also, the people that do the proof of space are different than the people that do the proof of time. We have these things called time lords, which are essentially parties that can compute the VDF. It's likely that really fast ASICs will be developed. So what we see likely is happening is that there's these parties that can charge to compute the VDF. In this blockchain, the rewards are given to the space farmers. They're not given to the VDF executors. So for example, if I have a really fast ASIC, I can actually charge to compute this VDF. However, for the system, you only need one honest time lord. As long as you have one honest person computing the VDF that is close enough to the attacker, then the system is secure. I'm going to explain again what happens if the attacker actually has a much faster ASIC, and that's one of the security assumptions that we have, the AMAX. So this is the general idea of how the blockchain is designed. There are some problems with this. So if the proof of space and proof of time are not unique, or if you have to include some data, like let's say transaction data, this allows for grinding. So let me explain. Let's say that in Bitcoin, all your data gets hashed into the block header. So the proof of work depends on the proof of blocks. Sorry, the proof of work depends on the data, right? If you change the transaction a little bit, your whole proof of work function changes. In this system, that wouldn't work. It would mean that a miner or a farmer would be able to change the transactions and get a new proof of space every time, and he could just choose the transaction that benefits him the most. So what we need to do is have two blockchains, one which is non-malleable at all. There's no way to actually change it. And the other one which is malleable, which has all the blockchain data. So So a farmer, recall that the farmer has a public key associated with him that's embedded into the space, into the plot. The farmer actually computes the proof of space based on the previous VDF. So let's say a VDF gets finished, it gets released to the network. A farmer now checks his hard drive using this challenge using the output from the last VDF, checks his hard drive, and notice that this does not depend on any transactions included. The proof of space only depends on the previous block's VDF, which is unique. At this point, the farmer only has one chance, right? They either they got a good proof or they got a bad proof. If they got a good proof, their VDF is small. If they got a bad proof, their VDF is really long, right? So at that point, the farmer creates this kind of block header, unique block header, which does not depend on the data, and releases it to the network. Later on, the farmer can actually submit the block. And the block actually has a signature using the same public key that was embedded in the proof of space and has a signature of the previous block. That means that the farmer could, in theory, sign multiple blocks at the same block height. This is a danger that can be mitigated by just waiting for more confirmations. So as long as, let's say you wait for 100 blocks, as long as one of these farmers was honest, that means that there's no way to reorg past that point, right? Because this guy only signed one block at that height. So it just requires waiting longer for confirmations. So basically, there's two blockchains. One is completely unique and cannot be validated, and one is not unique. So what does a space farmer do? First of all, he initializes the proof of space. This is an operation that is done once and takes a long time because it requires sorting on disk, sorting large amounts of data on disk. And then every time a new block gets released to the network, the farmer of a new block that contains proof of space and a VDF proof, the farmer updates the chain, the local state, and creates a signature. So this is a unique signature, which is another primitive that is necessary here. A unique signature of the VDF output of the previous block. And since this is a deterministic signature, there's only one challenge for the previous block. So the farmer gets his challenge, looks up the proof of space, which is a constant number of disk seeks, so it's very fast, creates a block, signs it, and updates it to the chain if it's a good proof, right? Most of the time, it's going to require trillions, quadrillions of iterations, so you just discard it. The algorithm for the Time Lords, which are the people that compute the VDF, is you initialize the chain, and every time you see a proof of space, you see if it's going to be completed first or completed really soon, and you execute the VDF. And then you propagate the VDF proof as soon as you have it. Another requirement here is that the VDF proof has to be really fast to compute. If the VDF proof takes as much time as computing the VDF, then that means that this Time Lord is inefficient compared to others. So another difference with Bitcoin in this algorithm is that a farmer can actually compute proofs of space on multiple blocks. With Bitcoin, the rule is you follow the shortest chain. Oh, sorry, you follow the longest chain, or the first one that comes out. So let's say this block is released in 5 minutes. The honest behavior of the protocol is that everyone just goes on this block, performs a proof of work or proof of space on this block. However, with proof of work, it's different. You can only work on one block. With proof of space, you can work on multiple blocks at once, right? So all the honest people only create a proof of space on this one. But an attacker can technically get all the other blocks that were released at the same height and perform a proof of space on all of them. And there's a chance that he gets lucky, and he gets one that actually can cause a reorg. So he gets a new block faster than the rest of the network can get the honest block. So we actually proved what is the advantage that the attacker gets if he follows all the blocks. And the advantage is actually E, so that's 2.718, which means that an attacker can multiply his space by 2.718 by following all the heads as opposed to following just the honest one. So to mitigate this attack, we can just change the honest protocol to be you follow the top 3 or top 5 blocks, right? So the first 5 blocks to come out, each person in the system computes their proof of space on all 5, and then releases them if they're good. This reduces the attacker's advantage significantly. There's still a trade-off here, right? You can't follow everything. You can only propagate a limited number of blocks. So that means that a 51% attack becomes a little bit easier to perform for the attacker, perhaps 45%, perhaps 40% to perform the same attack. So this is a trade-off with network bandwidth. Then there's work difficulty. I mentioned that the top chain is completely independent of any data in the blockchain, right? It's a completely separate blockchain with only proofs of space and proofs of VDF proofs. However, there is a difficulty, right, which actually affects how many iterations have to happen. And the difficulty is computed from the timestamps in the block. The timestamps are actually in the block data. So with a naive work difficulty algorithm in Bitcoin, basically the difficulty changes after a certain point, and then the difficulty is different right after that. So that wouldn't work for this system, because that means that the attacker could choose a timestamp that actually benefits him, right? Could choose a timestamp so that the next block gives him a really good proof of space. It's a grinding attack. So to fix this, we just make the difficulty adjustment kick in 500 blocks into the future, or a certain number of blocks into the future. That means that even if the attacker messes with the timestamps, he would have to compute 500 blocks worth of VDF in order to see whether that timestamp change actually helped him or hurt him. Also, there's a max difficulty change factor of 4, which is also quite important because there's an attack, if that's not the case. So that's the work difficulty algorithm. So in terms of VDF specifics, the proofs we're using are N-Wessolowski, so iterated Wessolowski, which Justin mentioned before. And this allows a really good trade-off between proof computation time and the size. So the size of the proof is only one group element, and the time to compute the proof is going to be like almost negligible compared to the VDF computation time. And actually, we're using class groups. Our plan for this blockchain is to use class groups as opposed to RSA groups. And the reason is we need a group of unknown order, but we don't want to go through the trusted setup and the RSA ceremony. So these class groups allow you to create a group of unknown order really easily by just creating a prime, a large prime. And it's unknown how to actually compute the order. And the best attacks, I believe, are about square root of the prime. Also, these attacks are actually a little bit weaker for class groups than for RSA groups. So potentially, you can reduce the size of the numbers that you're computing with class groups. Instead of 3,000 bits, maybe you can use 2,000 bits. Another benefit is that since we can create these groups as much as we want, they don't require trusted setup, we can change the group every single block. So using the output of the VDF, we have randomness essentially, so we can use that to generate a prime, deterministically generate a prime. And using that prime, we create a new class group. So each block, we have a brand new group. And the input to the VDF is, well, the element that you're squaring is the same every single time. All we change is the group that it's in. This allows us to further reduce the size of the numbers, right? Because we can change the group every 5 minutes, so an attacker only has a very limited amount of time to break the group, to find the order of the group. We have an algorithm for squaring that we've optimized in CPU, and we ran 2 competitions optimizing the algorithm. It requires a partial GDC, and the algorithm is called Nuduple. And we plan to do FPGA and ASIC competitions as well in the future. So the same as Ethereum, we want to optimize this as much as possible, right? Because an attacker can damage the system significantly if he can get a much faster implementation. So regarding that, the most obvious attack here is that the attacker can develop a faster ASIC, let's say 2 times faster ASIC, and therefore his block times will be shorter. So actually, it can be proved that a 2 times faster VDF can get you roughly, can allow you to pretend you have 2 times as much space, right? So a 51% attack becomes much easier to perform if you have a faster VDF. So this is one of the problems with the system. We can't allow an attacker to get a much higher advantage. That's why we really care about open sourcing ASIC designs, and we plan to continue doing these competitions and hope that like all the research into these ASIC algorithms becomes open source. Furthermore, VDF competition can be sold as a service. There's a lot of analysis to be done on whether they have incentive to sell and how they set prices. depending on who has the fastest VDF, considering they don't get rewards in the system. Then there's a lot of attacks regarding proof of space. If the proof of space doesn't have the properties that I described earlier, there's attacks. And since it's Nakamoto Consensus, there's a 51% attack. And there is a selfish farming attacks, same as selfish mining attacks. And there's still analysis left to be done on how selfish farming attacks differ from selfish mining attacks. But there does seem to be benefit there. That's basically it. I hope it was easy to understand, and I can answer any questions.
On that non-malleable chain, is that thing, I'm assuming that's like a global chain, that proof of, where's that proof of space coming from, I guess, in that? Is that whole chain sort of deterministic?
Yeah, this whole chain is deterministic. This proof of space is coming from each farmer's disk, right, which was initialized with their own private key.
So that is unique to each farmer?
Yeah, each farmer has a unique private key, and therefore they have a unique plot on their disk. Okay. So that determines the proof of space. It's kind of like your nonce in SHA-256, like your nonce in Bitcoin. You can set that to whatever you want, and that creates a different proof of space.
Okay, and this is where that I guess, forging the space comes up? Like, I'm just wondering, can they, if you have multiple VDFs and you can do this initialization of the proof of space very quick,
right?
Can you grind, is that where
yes, that's an attack, actually. If you get, so this is, if you can create this plot, if you can, let's say you have a 100 terabyte hard drive, if you can plot that really quickly, like in 1 second, then you can do that over and over until you get like a better proof of space. Right, so there's an assumption that it takes at least the block time to create your plot. And in practice, we don't see that there's any way to actually plot this faster than 5 minutes. Even if there is, you're not going to get much benefit from that because there's additional cost, right, to actually plotting this energy cost, and your hard drive is getting slower and things like that.
Okay, so you guys aren't thinking that that's like an attack, it's like grinding the proof of space?
No, I mean we know it's an attack, but we don't think it's practical, yeah.
If there is a ledger with transactions like A cents money to be in this scheme, how is it secure against double spends in a forked scenario?
So it's not secure against double spends in that this guy can sign 2 different blocks at the same height, right? And only one can be valid. So if anyone's sending money in these blocks, you have to wait a significant number of blocks. It has to be deep, right? If it's not deep, you don't know which one of those 2 blocks will win. It's kind of like in Bitcoin when 2 blocks come out. Both can be valid, right? You have to wait a significant number of confirmations.
But even if it's deep, it's no cost to create totally different blocks.
Right, it's no cost to create this one, but at some point there's going to be an honest block. Right, after the honest block, there's only one signature, so there's only one block at this height. You can't actually reorg these anymore, right? Because that requires changing this one.
So you're not secure against bribing sort of the following.
Right, if you bribe everyone, let's say there's you can set the threshold how you want. If it's 1,000 blocks, you would have to bribe every single one of those 1,000 to reorg. So yeah, it's a little bit different than Bitcoin's, right?
You're just assuming there is some honest participants and that they're incentivized not through money or whatever, they're going to only.
Right, I mean we have a 50% honest assumption, which is really important, right?
Which includes that's not necessarily economically honest or whatever, or economically rational.
Right,
it's
right.
honest in that they're not economically rational, perhaps.
Yeah. There's also things you can do with fraud proofs, like you could burn their block reward if there's two blocks of the same height, but that adds a lot of complexity. So.
I think we have to go on to the next speakers because you've run over time, but you can ask your questions at lunch.
Yes.
Thank you. Okay.
Thank you.